Good afternoon, everyone. Thank you for coming to this session on research and education talks as part of NANOG. We have 5 exciting talks today. 3 will be trying to talk about the difficult and challenging problem of wrangling BGP information, and 2 will talk about the DDoS mitigation and analysis techniques. First up is going to be Ruwaifa Anwar from Stony Brook University. He's a second-year PhD student at Stony Brook University, and he'll be talking to us about investigating interdomain routing and policies in the wild.
And I will get Raifa's slide set up for him. You can use this as your clicker, or you can use the keyboard, however you want to do it. And you are this one. Boom. There you go.
Hi everyone. So today I'll be focusing on how the paths predicted by the popular interdomain routing model compare with the real path. So researchers want to study the internet for various purposes. They want to study the internet to build new protocols and to test existing ones. For example, we might want to know how much security we can get from BGP-SEC before actually deploying it in the wild. Or what are the deployment challenges concerned with IPv6? So researchers want to study internet to test new ideas before actually putting them in practice, or to test the existing ones. Or maybe just to understand the implication of a policy. For example, back in early 2011, when Egyptian network providers were forced to withdraw their routes. But the problem is that we can't run experiments directly on the internet. It's not feasible to test half-baked ideas on the live internet. So we need to somehow simulate the behavior of various aspects of internet. We need something to play around with for all these what-if scenarios. So that's why we resort to internet models. So we resort to internet models as they fill in gaps in empirical data and allow simulations. So models like AS topology, routing policies, and traffic matrices are immensely popular among academics, and they have found basis for many research studies. So in this talk, we'll be focusing on models of routing policies, and the key question we try to reason is that what are the reasons that some of the paths generated by our models do not match those in real practice, or how many paths generated by a model really match the real path, and if there are any discrepancies, what are the reasons behind these discrepancies? So firstly, in this talk, I'll briefly explain the popular model, the Gore-Exford model, and the AS topology we used. Then I'll explain how we use network measurement platforms like RIPE Atlas and peering platform to target important and heavy traffic network paths. And finally, I will show the comparison with these network paths to paths predicted by the model and try to explain few reasons for discrepancies. While I'm going to present some reasons we found in our data, it would also be great to chat with folks after this talk if you want to talk about some interesting behaviors that you guys have been observing in your own networks. So the now standard model of routing policies was put forward by Ngao and Rexford in early 2011. So the model was based on routing policies of a large ISP at that time. According to this model, an AS can have 2 types of relationships. It can have a customer-provider relation in which the customer pays the transit cost, or it can have a peer-to-peer relation in which both ASs exchange traffic at no cost. So for path selection, the Gore-Exford model dictates that the customer path should be preferred over peer path, and a peer path should be preferred over a provider path. And for paths having same local pref, the shortest of all paths is picked according to this model. So as far as export policy is concerned, a customer path is exported to all neighbors. However, if there is a path from a peer or provider, according to the Gore-Exford model, it is exported to only customers. So note that this model only deals with inter-domain factors. That is, what's the business relationship between a pair of neighboring ASNs, And this model is sometimes augmented with assumption that ASs only consider the next hop AS on the AS path when making their routing decision. This obviously simplifies analysis and makes debugging more tractable. Having said that, this model is widely used in a lot of research studies by academics. So Keda measures BGP path through a bunch of route collectors from route views and RIPE, and then they use these paths to create AS topology using these three assumptions. So one of the assumptions is that most ASs engage into transit relation with other ASs to be globally reachable. Second assumption is that there is a clique of large transit providers or tier 1 ASs at the top of hierarchy. And third assumption is that cycles of customer provider links should not exist for routing to converge. So for each pair of AS, they infer the relation between the ASs, like which two ASNs have customer provider relation or which two ASNs have a peer-to-peer relation. So by the January of 2015, so this Keda topology had more than 52,000 nodes and more than 210,000 edges. So with this topology in place, from any AS, we can predict policy compliant paths. Okay, so we have seen how we model routing policies and the AS level topology. After this, we needed some real network paths to compare our models with. To do this, we used RIPE Atlas. So RIPE Atlas hosts thousands of probes across the globe. We can use these probes to carry out network measurements like trace routes, pings, and DNS requests. So we selected 2,000 RIPE Atlas probes evenly from different countries and different ASs. And then we selected top host in terms of most downstream bytes and visits. So this included popular content network like Facebook, Google, Amazon, and Netflix. So we selected these hosts as they carry bulk of internet traffic. We got the list of top application and websites from Comcast and Sandvine, from where we isolated HTTP and non-HTTP host. Finally, from each of these RIPE Atlas probes, we issued trace routes towards selected DNS names. And in the end, we had more than 28,000 trace routes towards 34 DNS names. Okay, so after trace routes and converting them to AS paths, we compare two types of AS path. One, the path we got from our trace routes that we got from RIPE Atlas, and other, the GAU-Rexford compliant paths we computed from KDOS topology. So for every hop in AS path, we computed what were the options the ASS had according to the topology, and what path did it actually take. So the figure on the right, it shows all possible paths according to the GAU-Rexford model or the path predicted by our model. And so the rightmost part is GAU-Rexford compliant cheapest or shortest path, or it's the path predicted by our model. If ASS takes this path, we would classify this kind of path as following our model, or in that case, our path prediction matched with the real path. But if ASS takes some other path that can be a longer path, or that can be expensive path, or even it can be a combination of both, then that part was not classified as GAU-Rexford path, or in that case, our path prediction didn't match the real path. So combined, for more than 65% of paths, we found our path predictions from that model and topology were actually following the real path. So for 65% of paths, so the paths were actually GAU-Rexford compliant. But still, there were 35% of paths in which our predictions went wrong. So what were the reason of our faulty predictions? Why our predicted paths didn't match the reality in these cases? So we'll look at this in the next few slides. So one thing about GAU-Rexford model is that it abstracts the inter-domain routing to the level of destination AS. However, as we know, that's not always the case. So ASs can employ prefix-specific policies. So just to give you guys an example of prefix-specific policies we observe and how the paths predicted didn't match the reality, consider this figure. So according to this topology, AS 35244 or KMS, it can take 2-hop path from its provider level 3 to Netflix. So this was the expected path. This is the path that was predicted by the Gower-Rexford model. But in reality, so what the observed path was that it was different. So instead of taking that 2-hop path towards Netflix, it took the 4-hop path toward that same host. And so what was the reason that why instead of taking a shorter path, it went for a 4-hop path? So when we looked at BGP feeds, we found that that particular prefix was never announced to level 3. So level 3 was provided for Netflix, but for that particular prefix, only XO communication received the announcement. So through BGP feeds and looking glass servers, we found additional 11% of decision following Gower-Rexford model, or for that cases, our path prediction matched the reality when we took into account the case of prefix vested policies. And another question that I was hoping to ask for you guys was that how often and for what reasons would operators employ prefix specific policies? It would be great to have chat on this topic after this talk. So we found undersea cables as reasons of faulty prediction too. So undersea cables confuse existing models because they do not originate their own traffic, and ASs on both ends pay the transit fees. So they in a way resemble high cost and high latency IXPs. So we could identify a few cable ASs from telegraphy maps. We included only those ASNs which are solely used for undersea cables, or we didn't include those AS numbers which were used for both undersea and land connection. So we did this because we wanted to isolate the impact of undersea cables in our study. So we found 2% of AS paths having undersea cable ASs, but out of these 2% of AS paths, more than half of the paths were not Gower-Rexford compliant, or in that case, our path prediction didn't match the real path that we observed. So that was one of the reasons. So next we focused on trace routes, where we inferred that entire trace route path stayed within a single country, but there was a better multinational path available according to the topology. So we define a multinational path, a path where at least one AS is registered in a country outside the country of source and destination AS. So we observed some cases where ASs went for an expensive option according to the topology, but there was a cheaper option available, but that included going outside the country of origin. So we found that path predictions were actually better when the whole trace route path stayed inside the country of origin. One obvious limitation of this approach is that even for the ASs that reside in multiple countries, the WHOIS data would still point to just one country. So in addition to prefix specific policies and impact of geography, we also looked at siblings and complex routing policies. So sibling ASs are those ASs which belong to same organization. They're controlled by one entity. While complex relation means those relations when a pair of AS has different relation according to different location. So a pair of ASN can be customer provider in one location, but they can be peer-to-peer in some other location. So while we found 65% of path predictions to be correct with vanilla Gower-Rexford model, but after taking into account these factors, we found almost 85% of decisions were following our path predictions. So this is like 20% increase in a decision being followed by Gower-Rexford model. So another reason behind faulty prediction that we found is that the routing model deals with inter-domain factors only. However, as we know, these factors are not the only ones in decision making. So to study the impact of inter-domain factors in BGP decisioning, we use the peering platform. So peering is an experimental platform that runs its own ASN and prefixes. We can announce our own prefixes and send BGP control messages. So peering is a sort of an experimental ASN for us. So as part of our experiment to study intra-domain factors, we first announced a prefix from one of the pairing location. Since this was the only announcement, so AST would take the path towards the pairing announcement through AS1. Then after 5 minutes, the same prefix is announced from all other locations. So now AST has two options, either to keep its routes towards the pairing prefix through AS1, or drop this path and route towards the new announcement, the same prefix through AS2. So AS2 had two options. So a path can change or a path cannot change. So if the path changed, we checked whether the new path is cheaper or shorter. If none of them was the case, we inferred AST used intra-domain costs as tiebreaker. However, if the path did not change, we again checked whether the existing path is cheaper or shorter according to the topology and the model. And if it wasn't the case again, then we inferred that AST used route age. So for these experiments, we found 17% of decisions were made on intra-domain tiebreakers or route age. So our path predictions would be wrong for these type of decisions because, as I mentioned earlier, the model only deals with inter-domain factors. So summing up everything, so we compared path predicted by the popular routing model with real network paths. We found majority of path prediction actually following the real path. So for more than 65% of decisions, the predictions according to the vanilla model were correct. Then we tried to find reasons for anomalies for remaining 35% of decisions. So we could explain few decisions by sibling ASNs, geography, prefix-specific policies, undersea cables, and domestic path preference. So after this, the accuracy of prediction actually jumped to 84% of total decisions. But still, few anomalies remain unanswered. So obviously, we need your help in understanding why some paths deviate from the model. Thank you so much, and if you guys have any question.
We have about 5 minutes for questions.
Hi, Nick Holt from Microsoft. What I saw you do was cut out areas where your prediction didn't align with the model, but I didn't really hear an explanation that, like, oh, there's a reason why intra-country doesn't route well, or there's a reason why the subsea cables don't route well. As far as BGP is concerned, those are just hops. So do you have a theory as to why something's changing, right? Vanilla BGP is not being used if cross-country boundaries actually come into the equation.
Yes, so we actually try to find reason that why they're so. For example, as I explained for undersea cables, so undersea cables they do not sort of fit into the routing model because ASs on both ends generally pay up the transit cost. So it's not like conventional customer-provider relation. So for undersea cable, maybe that's the reason. And for your other question that for why ASs were preferring path that stays inside their own country. So for that I don't really have an exact answer. Then that why is that so? Then maybe it's due to some policy, or maybe that data was important one or sensitive one that I don't want to send to other countries. So maybe there were some country-specific policies going on there. Thank you.
Randy Bush, IIJ. Cal Rexford was a model. There are people who didn't believe it in 2002. It's a model. Those aren't anomalies. That's the internet. The internet is highly varied. There are large providers who don't prefer customers. That's the way it is. Okay? There are lots of ways the model is, quote, broken, unquote, or that there are lots of anomalies, and that's the way it's going to be. It's not that they need to go out and be fixed. It's that it was a model. It covered 70%. That's not bad. My point on the Gow-Rexford model is, as computer scientists, we need something when we want to do simulations, et cetera, okay? So we take this model because it's the only one really out there, unless you want to get really ugly and complex, okay? That is fine if and only if you do sensitivity analysis to know that you are not dependent upon this model. Then it's fine. It's a model.
Okay, so yeah, so the purpose of this whole project was that, I mean, we were not trying to fix the model, or we're not trying to say that these are the improvements that if we do to the model, then it would work for everything. So as it,
Oh no, I
as
think
you
your
said, it's
study's great. It proved a point I've been trying to make for 15 years. You measured it. Thank you.
Doug Montgomery, I missed the point. Did you, through manual inspection, rationalize the difference that got you from 65 to 84%? Or can you algorithmically encode that so that you can now take in national borders, undersea cables, and specific addresses that are filtered along paths? Is your augmented model repeatable? Can you run it now and come up with 84% correspondence?
Yeah, it can work for the data that's available to us. For example, in case of prefix specific policies, we didn't have a lot of looking glass servers, and unfortunately we didn't have an API to look at looking glass server. So for that particular section, we sort of couldn't automate the result. But having employing the knowledge of sibling ASNs and prefix specific policies, this is sort of that goes with the model now. That goes with our algorithm. I'm not sure if I have answered your question
Do
correctly.
you have running code that takes what would have been predicted out of the Kata-Gao-Rexford model and produces an augmented one of those that factors in these other issues?
Yeah.
So you have running code that will do that.
Yeah, so basically, given the destination AS, it would predict that what should be the ideal path should be keeping into account the sibling ASNs and the prefix specific policies and these things.
And maybe related to Randy's comment, then have you done sensitivity analysis on that other than sort of one recent snapshot? Have you looked at past histories?
No, we haven't really looked at this thing a lot.
Hi, I'm Mingwei Zhang from University of Oregon. So I have a question regarding about your improvement of the modeling. So you said that you're taking consideration of 4 aspects. One is the prefix specific policies, and the other is the like more complex policies. So first, how do you get this policies data from other ASs, and how do you validate those policies are actually the ASs are using?
I see. So for the first question, how we got the complex data. So for that, there's actually a Kata data set that's public, which actually tells us the information that these 2 ASs paired at this location, and these 2 ASs paired at this particular, and these 2 ASs have different relation at this exact location. So for that, there is a data set that's available to everyone. And for the second question, for prefix specific policies, so we looked at the available looking glass servers to us, and we also looked at BGP feeds. So that's all we got.
So you look at the prefix announcements and how the different looking glasses had the routes.
Yeah. So
you infer that from those.
Yeah. So for example, for a target AS that we wanted to know whether it's doing prefix specific policies or not, we need to find a looking glass server at its next hop AS to exactly find out whether that particular prefix is being announced to this guy or not.
Thank you.
Thank you so much.
One last question. Do you have a name for the new model? Do you call it enhanced model?
Yeah, but again, as I said, that we're not trying to make a new model. So we're just trying to see where path predictions break, or what are the possible causes. So that was never the goal, just to make a new model that would work. So.
Last question.
Yeah, Jay Hennigan with Impulse. I think to Randy's point, it is a model, and you've got now over 65,000 ASs on the internet, and each of those has somebody in charge of making decisions. It could very well be that a particular link is being saturated and the person doesn't want to spend more money to upgrade that size of that link, and so they'll push traffic elsewhere. Without looking at something that doesn't match the model and going to who is and inquiring of the AS, why are you doing this? In which case probably you're going to get ignored 80% of the time, and 10% of the time you're going to get it's proprietary, none of your business, and maybe 10% of the time you might get an answer, and maybe half of those answers might be right. That I think the point is right. It is a model that it works as well as it does is a good thing. And so I don't know if you're ever going to be able to answer those questions.
Yeah, so I totally agree with a lot of points that you have made here. So when I started this whole talk, the whole motivation that I thought was that I presented was that. So this is a model that I completely agree. It won't do path prediction for 100% of paths. There would always be anomalies going on there. I think it's true for any model. For any model, it would never fit the real path. So what I was trying to make a point is that given that you have a model and you have your ACE topologies, and if you try to do the path prediction from this, how good or how bad you can be, or if there is something bad is going on, what is the reason behind this? And then still there were 15% anomalies that we couldn't sort of answer. Maybe these are one of the reasons that you were just explaining. Because again, it's a model. Any AS can do any kind of stuff that no model would predict. Yeah, but I agree. Thank you.
Thank you, Reva. I think as you come to more and more NANOG events, you will learn to use the phrase, according to the best available data. This is the best we can do. Next up, speaking of CADA, next up is Alberto from CADA and UCSD. He will be talking to us today about some work they're doing about BGP Stream, which allows you to do historical and real-time analysis of BGP data.
So, good afternoon. This is a joint work with Chiara Orsini and Alistair King. And I traveled from far today to talk to you about BGP Stream. There is a software framework for BGP data analysis that targets both research and operations, like, for example, live monitoring of BGP data. So BGP Stream was inspired and was actually needed for a couple of research projects that we started in CADA about 4 years ago, at least one of them 4 years ago, about monitoring the entire internet for detecting and characterizing large-scale events such as internet blackouts, outages, and hijacking events. So in few slides, I will show you a couple of examples. Here, this diagram shows a several countrywide internet outages that happened in Iraq in summer of last year, when allegedly the government ordered the internet shutdown, basically in conjunction with ministerial preparatory exams. The blue line that you see in the graph represents the number of prefixes geolocated to Iraq that were visible according to route views and RIPE risk collectors. And so when you see the line dropping down, it means basically that in practice, Iraq was disconnected. And the other color graphs that you see stacked represent the 5 top operators in Iraq, the same type of information for the 5 top operators. This other graph shows an outage of about 30 minutes of Time Warner cable a few months ago. The blue and the green line, respectively, represents IPv4 and IPv6 prefixes from this autonomous system of Time Warner cable. Again, when they go down, you see there is an outage, and we correlate this data from the control plane from BGP with data instead captured on the data plane. These bursty lines, noisy lines in orange and in red, they represent sources captured at 2 large darknets in the US that come from the same autonomous systems. This is another project. We called it Hijacks. It's not a very original name, but it's about detecting again and characterizing BGP hijacking events. and specifically man-in-the-middle attacks perpetrated through BGP hijacking. So these are attacks in which the hijacker then, once it receives the hijacked traffic, it routes the traffic to the legitimate destination. So in working on these projects, we had to develop a lot of software. We had to deploy some quite complex infrastructure to process huge amounts of data, different type of measurements data. As I said, from the control plane for BGP, data from route views and RIPRIs, but also data from the data plane, both data from passive monitors and data from active probing. The point of this slide is just to show you that BGP Stream was necessary for us. I mean, we just developed it because we found there was a gap in the state of the art. We needed some software to crunch a large amount of BGP data in real time in order to carry out these projects. So then we thought, okay, probably we can make this software available to the community as open source. That's what we did. So in April of last year, we introduced the project publicly. In May, we presented at the RIPE meeting in Amsterdam, and we announced and distributed a beta version. Then at the ITF meeting in Yokohama in November, we finally announced and published version 1.0. A few weeks ago, actually, a couple of weeks ago, we just released version 1.1. So you can go on the website, download it. The code is on GitHub. It's open source. So now, before talking in detail, I won't talk in detail about the project because we don't have time. But before giving you an overview of the software framework, I want to immediately give you an idea of how you can use it. Like, we used it for those projects. Of course, you can think about building complex infrastructure, or you can think about just monitoring, for example, your own address space. So I have a couple of slides of example. This is the first one. BGP Corsaro is one of the tools that are distributed with BGP Stream. It's a tool coded in C. It is designed to efficiently process large amounts of BGP data at regular intervals. So in time beans, let's say, of 1 minute or 5 minutes, it depends on the configuration. It will extract statistics. It will perform certain operations. And these operations are actually performed by plugins that operate in a pipeline. So it's a modular software. You can write your own plugins in C, or you can use plugins that we distribute already with the software, such as the one that I'm going to talk a little bit about it right now in this slide. You can modify our plugins. You can start working with it by modifying just existing plugins. So in this case, we show an example of the prefix monitor plugin, which basically what it does, it takes as input a set of IP ranges, and then it monitors BGP looking for prefixes that are announced, again, according to the sources that are used, for example, route views and RIPRIs, that overlap with the prefix range, with the address ranges that are given as input. And it also, and this is done at every time bean. So if you configure it to work every minute with time beans of 1 minute, every minute it will dump some statistics. The other information that will dump it is how many ASs are announcing prefixes that overlap with the address range given as input. And it, of course, will dump also some raw logs that you can use later for analysis. So what you see here in the graph is an example of probably a hijacking event. These are, in this case, we ran the prefix monitor plugin on the address ranges that normally are announced by AS137 GAR. And this is the prefix monitor running for the entire period of January 2015. So the green line that you see here represents the number of prefixes that overlap with the addresses normally announced by GAR. And then the blue line, the one with the 4 spikes, represents simply the number of origin ASs, that are announcing those prefixes. And when you see those spikes, the number bumps from 1 to 2. The blue line is, the values of the blue lines are on the right y-axis. So these events, these spikes, correspond to hijacking, to announcement from a Romanian AS that has nothing to do with GAR, which is instead the Italian Academic and Research Network, that announced a number few/24, the norm that belong to the address space of GAR, basically. And this event was actually reported by Dyn Research. So this is just an example of how you can use, out of the box, the prefix monitor plugin with Corsaro to, for example, monitor your address space. Of course, you can think about doing more complicated things. There are other plugins available. I will say it later. There is also a technical paper online. There are tutorials on the website. There is a technical paper where we explain how we used all the tools of the framework to build more complex infrastructure. But anyway, this is a totally different example. This shows instead how you can use Python bindings that we created. These are Python bindings to the main C library of the project. So you have the efficiency of code written in C, but the ease of using Python for your scripts. So we call the bindings PyBGP stream. This is an example that I use sometimes in presentations, but it's also on the website, I think. It's just a way of showing with so few lines, how with so few lines you can actually study a complex problem such as AS path inflation. So what this script does, it takes as input all the data from the rib dumps of route views and ripe risk collectors from, I think it's one day, probably the 1st of August of 2015. And it computes the difference between the actual paths between each monitor, each peer of the route views and ripe risk collectors and origin ASs unknowns in prefixes, and the shortest path. And so it calculates AS path inflation, which is depicted in the graph on the left. Basically, what the graph tells you that in 70% of the cases, we found that there was no path inflation. In the other 30, in the remaining 30% of the cases, there were there were from 1 up to 11 extra hops found on the internet. I mean, extra hops compared to the shortest path. You can even, I think we have a new example. I don't know if we put it on the website. You can probably code a lot of things that are done here by BGP Corsaro just in Python with few lines of Python code. BGP Readers is a command line tool, is very similar to the BGP dump tool that probably a lot of you know very well. It dumps data in ASCII format. It's very simple. Probably one of the most notable differences with BGP dump is that you can, with one command line, you can process data from multiple collectors, even from collectors of different projects, like from route views and ripe risk. And other differences will be clear in a few seconds. So this was just a super quick overview of tools that come out of BGP Stream. Now, briefly, how would we characterize BGP Stream? This is a very high-level view of the framework. So the graph here, this diagram, shows a high-level view, as I said, of the framework. At the bottom, we have on the left the metadata providers, and then on the right, the data providers. So the metadata provider by default is a web service called BGP Stream Broker that is developed by us, and it's actually it's on a Kita server. It's operated by us. You can also, we distribute the source code, so you can also deploy your own BGP Stream Broker. And it basically has a collection of metadata, and it keeps track of the data sources of the data provided by the data providers, like ripe risk and route views. So basically, the metadata distributed by the brokers is a set of pointers to the repositories where there is the actual data. So the main library, libbgp stream, is in the middle of the architecture, and it takes care of interrogating the broker and on the basis on the request from the user for the higher layers. So if you ask to a BGP Stream application to process data from a certain time interval and relate it to certain route collectors, automatically through the BGP Stream library, the application will download the data, actually will first query the broker, and then will download the data and will keep downloading the data from the data providers. So the streams are actually, let's say the stream of data is coming from the actual data providers. Then what the library does, though, it performs a sort of demultiplexing of this data, deserialization of this data, and then it tries to also perform a sorting of this data and providing a real-time stream to the upper layers. And the API is designed to make it simple for you to write applications or use our tools to process and to analyze BGP data. So without having to focus on which data you want to download and things like this. So on the top of the stack, there are the command line tools that I briefly mentioned, and an API in C and API in Python. On the website, there is a technical paper where you can find details about the design goals, design decisions for BGP Stream, how we engineered BGP Stream, the framework, and also there is more material, as I mentioned earlier, about how we used it in our research, right? So you will find the technical paper on the website. I just want to highlight a couple of points. So BGP Stream is designed to efficiently deal with large amounts of heterogeneous distributed data. It supports near real-time data processing. It targets a broad range of applications and users. So as I was saying, it's both for research, for educational purposes. You can use it in the classroom with Python, for example. And it targets, we believe, you should tell us, operational operations, like monitoring, for example. It is scalable, is designed to be deployed in a heavily distributed environment, but at the same time, you can just download it on your laptop and it should work out of the box. And it's easily extensible. So these are aspects that I would like to highlight. And then I invite you to go and check the paper or talk to us and give us feedback. Instead, I would like to use the few minutes left to give you a concrete example of what it means to make it easy with BGP, why BGP Stream makes it easy for you to access the data. So here in this slide, there are either the command line used by the command line tools or the few lines of code used by the C and the Python API that the user uses to specify which data he wants to access. So for example, on the left, there is the command line of BGP reader. With the -w option, you specify the time interval that you're interested in. With the C-C option, you specify which collector you want to get data from. In this case, it's routeviews.sfmix. And the -t indicates that you just want to process update dumps, for example. The same syntax is used on the command line on the right from BGP Corsaro. In this case, we put -p to specify that we want all the data from the collectors of RIS. If I didn't put that option, it would have meant I want to get all the data that is available from route views and from RIS right now. Actually, there is a surprise. There is more data available. And then there are other examples about, instead, as I said, the Python API and the C API. So for example, in the C API, we specified one collector from route views and one collector from RIS. Here, if I omit the time intervals, what happens is that the BGP Stream application will work in real-time mode. Basically, the library will go into blocking mode, and we will keep polling the broker for data. And as new data becomes available, that data will be downloaded by libBGP Stream and will navigate to the upper layers, will be part of the stream. So one last thing that I wanted to mention, this is an experimental deployment to make BGP Stream access BGP generated data, because all the examples that I made were related to to route views and RIPRIS, for which we have typically a latency. I'm talking about the MRT files that are distributed, are published by these projects on the web. And so the typical delay that the application gets this data with is between 5 and 15, 20 minutes, right? But here we experimented actually for the BGP hackathon that we hosted last weekend in Kedah. We experimented with a BMP feed to obtain about 1 minute latency. So with the help of Tim Evans from Cisco and John Kemp from RouteViews, we had this experimental deployment. Here, basically, we used an MRT consumer that is developed using OpenBMP, the OpenBMP library, to export MRT files that then are accessed by the BGP Stream application. But we plan to support natively BMP with BGP Stream. So this is a list of BMP feeds that were provided to us, courtesy of RouteViews, Cisco, and Randy Bush. Unfortunately, we didn't have the Randy Bush logo to put here. I apologize. And this is the list of routers, the list of routers that are feeding this BMP data source. I want to make you notice that basically, all these BMP feeds are working already with all the installations of BGP Stream. You don't need to download a new version of BGP Stream to access this data. You just have to use the tag Kedah-BMP, and you can already access this data. So really, if you want to share a BMP feed with us, please contact us, talk to me, or at this email address. And an interesting thing will be that as soon as we set it up, all the BGP Stream users will already be able to access the data right away. And that's all. Thank you.
Manish from Quadmetrics. So one of the problems that often occurs in consumer systems is you end up with clients that are not able to consume the data as fast as the stream server is putting it out. How do you handle that situation in the cases where there are slow consumer clients?
Yeah, no, the idea is that the consumer does pull requests. So there is, basically that's how we handle it. So it's a pull model. It's polling. So if the consumer can't keep up, then it's a problem of the consumer. There are a lot of synchronization problems. I mean, you touched one of those. There are several synchronization problems that are explained in the paper. Basically, you will solve the problem in the traditional ways. You will have buffers, you will have a moving window, and at a certain point, you will lose data if the data is not there. But we designed the system in a way that at least the services are protected, and then the application needs to be sure to keep up. The framework is, as I said, it can be distributed very easily. So for one of the projects that I showed, for example, the project on BGP hijacks, where slides here? But anyway, yeah, for this project, we have 32 BGP Corsaro running in parallel and processing data from different collectors. So one of the solutions is if your client can't keep up with that huge amount of data, just distribute the clients and then merge the data at a certain point. But the framework is developed in C, so it's quite fast. I'm confident that it can work in a lot of tough contexts.
Doug Montgomery, so if I'm just getting a stream of all the collectors, do I also get event notifications of sort of changes in metadata? You said, you know, as soon as someone adds a contributed stream, all the consumers get it instantly. Well, knowing that the set of producers has increased or decreased might be important.
No, okay, so as soon as new collectors, new data sources come out, you don't receive any notification. You can just go on the website and find that there are new types of data sources. Like there is a web page specifically for the broker that is automatically generated by the broker, where you can find all the types of data sources. As soon as new data from the collectors that you have already selected in command line or when you wrote your code, then that data, well, not as soon as it is available is transmitted, sorry. It's a pull model, as I was saying. So when the client is ready, the client will pull for new data and he will get it available. So it's like a subscribe service, a subscription service.
One of your examples looked like if I don't specify the set of collectors, I get them all. I get all the data sources. Is that true?
That's correct, but you will get all that are available at the time. Yes.
So if I'm feeding that into a real-time monitor and you have a glitch and some key data sources go offline, do I get an event notification?
No, I don't think so. Indeed, we have graphs that show when things are online. I think I know Emil could tell us more, but I think the collectors from Rypris have a state that is supported by BGP Stream. Also, thanks to his help, actually. But no, you don't have special event notifications. We were thinking about a signaling channel in parallel to the data channel. Yeah, that's something where we could think about.
Last question.
Anyway, John from University of Oregon. So it's great to, I've been lucky to play with it for several days. And one question that I have in mind is that it seems to be a server client model, which a client pulls data from the server. And how reliable is this server side? Like, do you put?
It's super reliable.
It's super reliable. Okay.
It's unbreakable.
So basically, if we run any applications on top of BGP Stream, we have to rely on the BGP Stream broker.
Yeah.
To provide the data.
Yeah, in the paper there is a whole section about how we design the broker to not be breakable. Seriously, I think it works. I'm not able to discuss it here now in 30 seconds, so we can take it offline. But really, we put a lot of thought in exactly that question. So the way the pull requests from the client to the broker are designed to protect the service. For example, you cannot flood with requests the broker. Each request must be done in batches, so if the client wants to get a huge amount of data, it won't be a single request. Requests will have to be chopped in batches, as I said. So there are mechanisms to protect the broker.
And you can
and
also install that in your
100%.
own server, right? You can.
Sorry?
You can also install an instance on your own site, right? The data broker.
Yeah, you can decide to install a broker instance on your system, on your network for a couple of reasons. Either because you want to have control on how the data is routed. You can also use it for doing a sort of load balancing. For example, if we query the broker from CADA, we get the data from a local repository and mirror of route views and right priest. We don't download their data again. Or you could do it because you have private data and you don't want to share it with the rest of the world. And so you can either configure your own broker and run our code, because as I said, it's available, or you can use simpler systems like these CSV and SQLite approaches that are there in the metadata provider with the symbol of the home.
Thank you.
Sure.
Absolutely, the last question.
Jay with Impulse, just curious if you have considered any scalability concerns for the collectors. If this becomes extremely popular and everyone in NANOG starts to run this in multiple places, will the route servers support that?
Where is John Kemp? He's here. Yeah. We've been discussing this with John, with the ripe risk guys. I think we will keep up. We'll do whatever we can with keep up. The broker, as I said, can work as a load balancer. So that gives us also some hope that we won't flood the guys that were so kindly making available this data to everybody. So we'll pay attention to do that. Actually, SDSC, I mean, CADA is part of SDSC, the San Diego Supercomputing Center. We have a lot of bandwidth, so we can think also about mirroring and providing a mirror from our broker. Next to the broker, I mean, there would be a mirror of the actual data providers, and we had these internal discussions about that. We are ready to do it anytime. So definitely our first concern is to protect these services that are vital. I didn't mention it, but actually here there has been, for the development of this work, I'm very happy because there has been a lot of joint work and coordination with the guys at Route Views and Right Priest. Maybe you have imagined from the presentation, but I didn't say it explicitly, so you give me the opportunity to say it. I know I need to cut it. We did a lot of work together. We tried to coordinate. We'll keep doing it. That's all. Thank you.
Thank you, Alberto. I think it's a good sign when people start asking questions about scalability because they like it. Next up, the next speaker is going to be Vincente De Luca from Zendesk, as well as Shafiq Peck. They'll be talking about some open source solutions they have stitched together for DDoS detection and mitigation.
Hi everybody, my name is Shafiq Peck, lead network engineer with Zendesk Incorporated. For those of you who are not familiar with what Zendesk is, we are a SaaS help desk service platform. And so we rely on the internet to run our business. And one of the main topic that we're going to discuss today is something that's affected just about anyone who's ever tried to run a business on the internet, and that's DDoS. We're not going to necessarily get into mitigation, but more of detection and taking action on the anomaly detection. And that's it's kind of, which has kind of been the biggest pain point for us is actually we've had a very slow manual process of DDoS detection, which takes sometimes minutes to in some cases it's been hours. And so I'm going to introduce to you Vicente De Luca, who's been a mastermind on putting a bunch of open source tools together to kind of automate our DDoS detection and move us into mitigation, sometimes within seconds and without even bringing up any sort of incident. So let me introduce Vicente De Luca.
Thank you. First of all, thank you, Manish, and all the NANOG program committee for having us here, and thanks for hiring me. So first of all, as Shafiq said, our main goal here is a tentative to solve in a fast way a DDoS detection and also give us some view, some monitoring on our traffic patterns and BPS, PPS, flow amounts. And also, after detecting a possible attack, improve the response time on triggering any mitigation technique available. So I will start right with the open source recipe. There is no secret. You can download all of those softwares. They're all available mostly on GitHub. So the main thing that we'll be talking about will be FastNetMon. How many of you guys know FastNetMon or use FastNetMon already? Oh, nice. Good. So we're using time series DB for storing all the metrics that FastNetMon processes. We're using Grafana for print and cool dashboards. Redis, which is a sort of a memory database that persists on disk. Morgoth, which is an anomaly detection. Bird, I presume everybody knows Bird's BGP daemon. And NetHealer, which is our own code to glue all those moving parts together. And we're going to cover each of them in a bit of detail here. So starting with FastNetMon, it's a very fast detection that relies on NetFlow, SFlow, or port mirroring. So it supports different capture backends, and so it's adaptable to your network environment. It might work for mostly of you guys here. You can collect from switch, from routers. It also supports shipping that process data to a Graphite database. Supports BGP daemon, so you can use these alerts or the detection to trigger BGP announce or a community or flow spec. It supports Lua, so if you want to post-process your NetFlow packets, you can also use Lua for it. And it's tested across a lot of Linux distribution, Unix servers, and tested with a bunch of different hardwares, network devices like Juniper, Cisco, Huawei, etc. So how the detection logic works, basically FastNetMon relies on thresholds. We're talking about thresholds. So if you know the amount of PPS, megabits per second, or flow targeting on a specific /32 of your network, that's good. That's all you need to use FastNetMon and detect. So let's say you are an ISP and you expect 200 megabits for a specific IP. If you're receiving 1 gigabit, well, that's not okay. So it's probably an attack. And there are some other things that happens under the hood that counts the amount of SIM packets, fragmented packets. So it basically supports detection to all the channel overflow, the mostly known attacks like SIM flood, UDP flood, amplified or not, and IP fragmentation. So how FastNetMon can react when it detects an attack? Basically, it calls a custom script that you can use to send an email, apply a router ACLO, or shut down a virtual machine if the attack is being originated on your network. You can use this custom script to do whatever you want, or you can use the integration with BGP to advertise a route. And it also populates the Redis database with the key containing all the attack details for you. So this is a detection time per capture backends. You guys can see that NetFlow is the most slow here. It takes around 40 seconds to detect. SFlow with around 2-3 seconds. And port metering is the best for detection in terms of speed, right? So this is our proof of concept that we've been developing at Zendesk, relying on FastNetMon. So if you guys don't know, this is Zendesk. We don't like to call it, but it's basically a ticket system where you can create tickets and have a better interaction with your customers. So first question is, why are we targets? Is that people hate Zendesk? No, that's not correct. But when you sign up for our product, you probably want to forward by use a CNAME, use an alias to forward support.your-domain to our data center, which is a good practice because if your website it's down, you're suffering an outage, your customers are still able to reach the support center and create a ticket and provide you information for help and troubleshooting. But when we do that, if someone attacks support.acme.com, you're not receiving the attack, and I am receiving the attack, and you as a customer expect that we have 100% availability, so we need to take care of this. So before this project, before FastNetMon and this NetHealer project internally, how the things were working. So good, bad, and the ugly. The good was mitigation. Mitigation always worked really satisfactory at Zendesk. We are relying on cloud mitigation providers. So we basically have a BGP session with them using IXP to have a GRE tunnel to have this BGP. And if we receive an attack, we advertise the /24 containing the target IP through this scrubbing center. They clean and send this back clean. So this works really well. I would say that 100% of the attacks that we received, they were able to mitigate the 100% time. So there's nothing to change here. There are some cons, which is the reaction time. It needs to wait for the BGP convergence, which is not that bad. Mitigation occurs on incoming only. We as a software company that have a controlled environment, we do not expect to originate an attack, but we also monitor that just in case. And the other cons is if you have it always on, it increase your latency and a little bit, but it's also really pricey for an always on solution. So the bad thing was that our NOC and our network team was getting pages when the site was down. So our face page was, okay, the whole data center is down. And that's not what we want, right? And the ugly part of it is that the detection was taking too long and all dependent on humans. So it was like, okay, my site is down. What's going on? I need to check graphs. I need to check logs and identify a spike or some firewall logs that was telling me about DDoS violation. Well, it was not working in the way that we wanted. So another question is, why not simple buy a DDoS mitigation appliance? First of all, mostly depend like you have a dedicated engineering team, well trained to operate those boxes. Mitigation available is useless in terms of channel overflow. So if you buy those boxes, you still need something else like a cloud provider in case they are doing a UDP flood that is more than your pipes, that is higher than your pipes. And it's a high, considerable investment for when you're talking about multiple sites. So the diagram of the whole solution is basically, at the left side, we have like a hardware physical diagram, and inside the circle is the Linux processes that are taking care of this. So basically, we have two edge routers here exporting all the net flow or S flow, it depends on the vendor, to a Linux box, a virtual machine. In our case, this virtual machine is 8 gigabytes of RAM and 8 CPU, and that's more than enough. Inside this Linux box, we run fastnetmon, which is collecting the net flow or any flow data. Fastnetmon is feeding an InfluxDB, which is a graphite-compatible database. It's also feeding a Redis database in case of an attack. And NetHealer, which is our own code, it reads both databases and it takes decision based on what those database contains, which can be send an email or page the network on call or just advertise automatically our prefix to enable the mitigation. So that's the entire diagram on how it works overview. So how is the attack cycle? So it starts with an attack, of course. So fastnetmon will detect it and will populate the details on our Redis database. So we also run Morgoth, which is an anomaly detection. Since we are not relying, as a software company or a content provider, you cannot predict well your threshold. So for today, you're consuming as a customer 200 megabits. Tomorrow, you'll start having issue. A lot of customers reaching your support center. So this traffic can spike to 1 gigabit, and this is legit. So I cannot rely really well on threshold. So this is why we're running Morgoth, trying to detect anomaly. We're going to cover in a bit detail. So NetHealer is watching those both databases, and if it finds an attack report that matches any of the defined policy, it will trigger an action that is associated with that policy. And let's say that fastnetmon detected an attack, it went through the cycle to populate, it will sleep for 15 seconds. So this 15 seconds is configurable. You can increase or decrease, and this will increase or decrease the sensitivity as well. So we found out that 15 seconds is okay for us, but we might want to lower it a little bit. So that means fastnetmon will sleep for 15 seconds, and after that, if the attack still remains, it's gonna keep that cycle going. So examples of NetHealer policies are, if there are 2 or more than 2 attacks in the last 5 minutes, trigger the network engineer on call. If there is more than 4, well, so let's inject a /24 route automatically. So I expect that the network engineer who was paged, when he comes online, let's say the airplane is already flying back on autopilot, stabilize it. So it's still our paging our network guy, but he doesn't need to apply any manual change to engage the mitigation. So if we find an attack from FastNetMon and also an anomaly detected on our time series DB, well, that's really no good. So we're gonna trigger on call and inject the /24 route at the same time. So time window and policies can be customized. This is for our Ruby code. It's not really well friendly. I would say that it's an experimental code, but you can customize all those policies in the way that you want and build your own as well. So why NetHealer? As I said, FastNetMon supports all I need. If you're an ISP and you want to run this software for triggering mitigation, automating, you don't need NetHealer because you probably know your thresholds. But in our case, since we don't, we needed to find an alternative to avoid false positives. I don't want to engage a mitigation in case of a little spike that my customer received, which is not an attack. So, and it also, building this internal software, it helped us to quickly integrate with other APIs like PagerDuty or creating this consensus between anomaly and FastNetMon detection. So we found it easier to build this code. Why InfluxDB? So I presume a lot of people here knows Graphite. Graphite is really cool, but it's a pain when you're talking about scaling. So we simply decided to go for InfluxDB, which is a drop-in binary. It supports Graphite protocol. If you're trying to reproduce this setup, I would suggest you to go to the version. When I did that slide was 0.96, now it's 0.10.0. So make sure you're running the last code because the previous one was suffering memory leak and it was a pain. So why Morgoth? So like I said, Morgoth implements a non-Gaussian algorithm for detecting anomaly on data. It basically works by taking fingerprints every 10 seconds, every chunk of 10 seconds, and storing that fingerprints on a database. So on upcoming traffic fingerprints, it's always comparing the actual with the past ones. And if it finds that it's really discrepancy, it will mark as an anomaly fingerprint and it will raise an alarm. So that's a note here. At the time that we developed this project, we relied on Morgoth, but now there is a software from the same company as InfluxDB, which is called Capacity, and it promised to do the same. So I would love to test, and if you guys are trying to build something like this, you might want to test Influx Capacity instead of Morgoth, which is a really immature and premature code, I would say that way. Why Bird? Well, that dispenses any comment. I think it works really well. It's really friendly to network engineers. The way that we've been using for this project, we sync the kernel routing table with Bird. So for advertising the prefix, it's just a matter of running route add, blah, 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 and as a simple Linux command. So you don't need to trigger API. It's super simple and it works really well. And you can use Bird for advertising black holes or for engaging the mitigation provider if you have it. So how does the overall thing looks? So this is a dashboard. This is a Grafana querying the InfluxDB. This is packets per second on our data centers. In this case here, we had no attack. So I put this screenshot to show that the tool is not useful only for detection, but also for monitoring. If you want to quickly know the amount of packets per second or megabits per globally or per IP or per host group, you can draw a dashboard on Grafana and follow that. So this is another example on packets per second flow amount. There is no attack here. You can have graphs per /30/24 or /23 or supernets. So it's easy to identify which network is spiking on traffic if you need to isolate it. And there we go. So here was a legit attack targeting our network. So if you know, I'm not sure, yeah, you're able to note a purple vertical bar on the graph. So at that stage, it was Morgoth detecting an anomaly. So we use this vertical bars to identify when the solution detected an anomaly or not. And as you can see here, it took around 9 minutes to fully mitigate it. So this is because we are relying on NetFlow, which is 40 seconds to detect. And after that, we need to engage the cloud mitigation provider. So the traffic converts to them, they analyze that, and they finally apply the filter for that specific vector. So these 9 minutes might sound like an eternity, but considering that in the past we had 40 minutes, 50 minutes, maybe more than an hour, we consider this as a huge improvement. And with the knowledge that we've been gaining with this project, I feel like we can easily bring this down to at least 5 minutes, just playing with timers and making it more sensitive, you know. So here's another attack that we received. So again, we had the purple vertical bars that shows an anomaly detection. It was exactly the same amount of time, so around 9 minutes from the attack start to the full mitigation. NetHealer also provides you an API, so REST API, so you can query the current status of your data center. If it's clear, if it's warning, if it's critical, it tells you the targets and the amount of the attack reports detected. It also tells you all a bunch of details like the attack direction, protocol, the peaks on PPS, megabits. So you can use those data available on REST API to populate a cool dashboard or something. And as I mentioned, this is a work in progress. All the ingredients is open source. If you want to reproduce, the first steps are read the documentation, download FastNetMon, and join the FastNetMon mail list. Pavel, who is the FastNetMon author, me, and the whole community will be more than happy to help you succeed on your implementation. And as I mentioned, NetHealer, the software that we internally develop, it's also open source. It's available on GitHub, but be aware that it's a pre-alpha code. So if you want to test it, feel free. Thank you. Any questions? Oh, you again. Good to see you, Alexander.
Hi, Vincent.
Hi.
Alexander Lemon, Curator Labs. Maybe get to the title slide.
Which one?
First ever slide.
First what?
First slide. Yes, this
the
one.
First one.
Yeah, first one. The title slide. So we can see the pink lines. This is anomaly detected, and after the anomaly resolved, we can see quite a bit of extra traffic than you had before. So what is that? Any ideas?
I'm sorry, I didn't get your question. So
After the anomaly was resolved, you can see quite a bit more of the normal traffic than you had before.
oh, the higher traffic after it.
Yes. Any ideas what is that?
I think this is related because we activated the mitigation. The mitigation means all of my traffic it's coming through a GRE tunnel, so I have an overhead, right? So I think that explains why we had more traffic after the mitigation was applied than before, because we do have an overhead on the tunneling stuff.
Or it wasn't fully mitigated. And then
Well,
the second question,
that's one point as well.
then
it
the
can
second
be-
question comes, it's all fine and dandy with current kind of amplification bandwidth attacks, but what you do is application layer. Because it's always like an armor vs guns competition, and whenever we figure out how we mitigate volumetric attacks, the layer 7 will get back on us. So how you do with layer 7 attacks, application layer?
So at layer 7, we do not rely on FastNetMon. We have other security products closer to the application that takes care of it. And to be honest, it's not something that happens often, not like amplification attacks or SIM flutes. So it's not, I would say for us, network engineers, we have a security team who takes care of those devices. For us, network engineers, it's not a major concern because it's not been, for now, not been offensive to our product, but we take care of this as well.
And I have to give you credit, wonderful use of open source tools. Amazing.
Thank you.
Jeff Stout, Akamai. Question I had for you was in regards to NetFlow. Are you taking, what is your mapping and your sampling rate? Are you looking at 1:1, 1 to 1024? Also, along those same lines, beyond just net flow statistics as a feed, are you looking at other vectors as well, like SNMP or different types of querying mechanisms? Because even you noted in your deck, traffic modeling is not always the best predictable amount, especially if you're getting flash crowds or unable to say, okay, because sometimes spikes are a good thing, right?
Yeah, so about the sampling rate, we've been using one of one. Our edge router supports without major suffering, so we've been exporting everything one-on-one. And FastNetMon is able, with a single virtual machine, to collect and process that data. And about the second question, I'm not sure if I understood. Would you mind repeating?
So beyond NetFlow, are you looking at any other ways to sample that data to get more visibility into that? Because NetFlow is only going to give you a certain amount of information.
Yes. So for this detection system, no, we're just relying on NetFlow. But we also have another, I would say, appliance in place which queries both flow, SNMP, and a lot of stuff. But we rely mostly on, for automating the mitigation, we've been relying on pure NetFlow. But if we need further inspection on something, then we have an appliance who does SNMP and query like interface counters and errors and packet drops and a lot of other stuff that NetFlow doesn't tell us. But for automating, we've been just relying on flows.
Tim Battles, AT&T. I was going to ask the same question about the flow rates that you're having. So you're doing one-to-one. Have you tested anything higher? And were you successful or unsuccessful at those higher sampling rates?
Yeah, I've tried higher, and it works in the same. The only difference, if you see on the graph here, it's more, to be honest, on the detection for FastNetMon, it doesn't change that much if you use like one of 2048 or something like that. It doesn't change. What it's gonna change is the graph, the time series that it is the result of FastNetMon processing. It's gonna be more, I don't know the word in English, but it's gonna be more, it's not accurate,
density,
yeah. It's not round graphs, it's less information. So if the edge router supports and your virtual machine is able to process, then do one-of-one, and you have more accuracy on the metrics that are processed. So.
All right. Then second question, how many router sources were you using, and what was the flows per second?
So how many routers?
How many router sources were you collecting
two edge
from?
routers sending to a single virtual machine.
So you didn't, in other words, for a scale question, if you had many routers and many flows per second, and you overwhelm that machine, is there a collaborative type engine that you're looking at when you have multiple collectors?
Yeah, what we can, FastNetMon supports multiple collectors per server, and also you can distribute on a variety of servers. So you can.
But are they collaborative between one another?
Well, actually, if you point all of them to the same Redis database, then you can build your code to take advantage of it. So
I got you. So
it depends on how you do your code.
Gotcha.
But you can do a collaborative environment. So you have a single Redis DB or a single cluster of Redis DB, and you point all of the FastNetMon collectors to that single database. So you fetch a single database, and you have information from all of your network.
All right. Good job.
Thank you.
Last question.
All right, Troy Jessup, UEN. My question actually is, how effective are the cloud-based services that you're using for mitigation? And have you looked at providing or digging into an open source tool or service to do your own mitigation?
So, like I said, all of the cases, all of the attacks that we received, the mitigation provider was successful, was responding, and we always want it faster than it is, but considering the business model and the response time and all the support, we are really, I would say, really satisfied, right, with their solution. But we also are always looking for alternatives and building stuff like there is like a thing called Symbro, I think Symbro.org. So we've been looking, Isolari, I think the guys will be doing a talk next to this one. So not only on the mitigation side, but on BGP analysis and stuff, we're always open to try different alternatives. So.
No, that's great. I was only mentioning it because, you know, a 9-minute lag time is still a long time. And so auto mitigation is how we had to get to the point where we're mitigating it ourselves in order to get those time frames down to something meaningful. But
Yeah,
good job.
one
Thank
thing
you.
that might be great is when all the upstream provider supports flows pack, then we'll make our life really easier, you know.
Amen.
Hi, how are you,
Hey,
Luca? Aurelio
how's it
from
going?
Thousand Eyes. So first of all, congratulations for the project.
Thank you.
If you try to do the same thing that you have accomplished here with a provider, when you engage with a DDoS provider that try to sell you a very expensive box, this is just for free. So it may have its flaws, but I think it's a great thing that you have accomplished. So
Really
my
glad to
question
hear.
was how easy it was with to engage when engaging with your DDoS cloud provider to get them to get to the point, you know, to understand that you want to automate that. Because sometimes, yeah, and in my experience, they might, you know, they might tend to ask you, no, just better do a phone call, you know, stuff like that. So they got, you know,
The
so
current
how easy
process
was
that-
the automation part with your?
Yeah, the thing is, since we've been paging the network engineer on call before automating the mitigation, so the process never changed in terms of getting the mitigation provider on phone, even with the automation. We want to follow close what's going on, what's the vector, what are the possible origins. So we are still keeping the phone calls on part of our room book. So the only thing is that we try to provide the network engineer on call more information about what's going on. So he receives a page containing the IP that it's target, the possible attack vector. So when he receives a page, he already have an idea on what's going on. So he can provide that information really quickly for the mitigation provider, instead of trying to troubleshoot and understand and then engage the guys and do the manual change on the router. So like I said, there's a lot of improvements to be done. I would love to have like an API call that you can just do an API call for the vendor and they will have all this data available instead of a telephone call, but that's not how it works today.
The one thing I do want to
Congrats.
add is that typically we do route on before we make any phone calls. So we allow the third-party provider to know that, you know, they've been really well, doing a great job with allowing us to route on before we even pick up the phone and call them. So.
All right, thanks, man.
Thank you.
Thank you. That was excellent. Gives full stack network developer a whole new meaning. Next up, Saeed. He's a PhD candidate at CMU. He'll be talking about flexible and elastic DDoS defense.
Thanks for the introduction. So how can we significantly improve the current practice of DDoS defense? I'm going to be talking about Bohate, which is an early promising step we've taken to answer that question. Bohate is essentially a DDoS mitigation system, and what it does, it brings the much needed flexibility and elasticity to the practice of DDoS defense. It's an open source system, and you can find the details of the work in the paper that has been recently published in the Usenix Security Symposium. Okay, but first, why DDoS? We all know that the cost of DDoS is significant for its victims in terms of monetary cost and reputation, but that's nothing new. That's pretty much true of any other attack, and DDoS has been around for a long time. The reason we got interested in this problem is that things are getting really out of hands on three fronts. The first problem is that the frequency or the number of attacks is increasing. For example, half of the companies in North America experience more than 5 DDoS attacks a year, and this number is going up. The second trend that we observe is the volume of attacks is also increasing. These days, we keep hearing of attacks of hundreds of gigabits per second, and these are the types of numbers that we couldn't think of just a few years back, but now they are the new reality. And to top it off, also the diversity of attacks is increasing. And what I mean by that is we are still struggling with traditional attacks like SYN flood and UDP flood. And on top of that, we are observing new emergent types of attacks and also new variations of existing attacks. For example, there are all sorts of different variations of, for example, amplification attacks. Now, this is essentially a snapshot of the existing attack landscape, which is quite horrible. So the natural question is, what are we actually doing today defense-wise? So let's take a look at the current practice. So this is a simplified view of how we do DDoS defense today. Essentially what we do is we buy these expensive proprietary hardware appliances, we deploy them at our networks, and we keep our fingers crossed hoping that things will work out. But unfortunately, like I just discussed, the reality is different. So let's look at the limitations of existing practice. The first limitation is these boxes have fixed functionality with respect to the types of attacks they can handle. So here I'm using different colors to indicate different types of attacks like SYN flood, UDP flood, DNS amplification. Now what happens here is if I buy one of these expensive boxes which happen to be blue, well, it can mitigate attacks of type blue. But what if I happen to be receiving orange or red attacks? Well, the box is useless. The second limitation is with respect to the capacity of these appliances that are fixed with respect to attack volume. So even if the attack is blue, my appliance is useful only up until a certain limit of sort of attack volume. So the moment attack volume exceeds the capacity of my box, again, the attack system is going to be useless. And the third limitation is that these boxes have to be deployed at fixed locations naturally because they are physical appliances. So I have to choose a location. Sometimes they are referred to as traffic choke points. Now the problem here is if I want to send traffic from the source to the destination that I'm showing here, instead of taking the shortest path or whatever the optimal path that my policy happened to mandate, I have to steer traffic all the way so that it goes through this defense appliance for DDoS defense vetting. This is inefficient for applications that I'm running at endpoints. And the other problem with this practice is to make this happen, I have to do all sorts of BGP hacks and other protocol hacks just to get this kind of routing in place, which is error prone and it can lead to all other types of problems. So what we need in reality is essentially the complete opposite of today's practice. We need flexibility and we need elasticity. What I mean by that is first we want to have flexibility with respect to attack type. So if the attack type is blue or orange or red, I want to have the ability to handle that kind of attack. We also want to have flexibility with respect to attack location. So instead of sending all the traffic to a fixed choke point, which is inefficient, I want to be able to naturally deploy my defense capacity at whatever ingress point that I happen to be receiving my attack traffic, be it point A or B or C. I want to have my defense there. And finally, we want to have elasticity with respect to attack volume, meaning that I would like to be able to naturally increase my defense capacity as the attack volume increases, and I want to do so elastically. And that is what we achieve using our system called Bohate. It's a practical ISP scale system for flexible and elastic DDoS defense. There are two key enablers for what we do. One is software-defined networking or SDN. The other is network functions virtualization or NFV. And just to give you an idea of what we achieve by doing this, our system can react to attacks of 500 gigabits per second just in the matter of a minute. But how do we do that? So let's consider an ISP that is trying to do DDoS defense. So ISP is a good example for a lot of reasons. First of all, an ISP is a good location to deploy a defense system, especially if it is a top-tier ISP. And also, we envision that ISPs can provide their customers with DDoS defense as an added value service, like pretty much like any other services that they provide their customers with. And a simplified view of ISP, we can think of it as a bunch of basically backbone routers and links, and recently a lot of ISPs have been rolling out data centers for their compute capacities that they can use for different reasons. Our system has 3 components. First thing we need is a prediction strategy. So whenever we want to be able to defend against DDoS attacks, first thing we need is a way of estimating the attack scenario, meaning that what volume, what type of attack we should be expecting to receive, and at which ingress points of the network. So that's what I mean by prediction. Now, given these estimates, the second thing we need is a way of doing resource management. And the reason for that is, on the one hand, we have the resources of the ISP, which is the bandwidth and the compute capacity of the data centers, and we want to essentially assign them to the task of DDoS defense that involves routing suspicious traffic around the ISP and launching defense virtual machines. And finally, having made these decisions, we also need an orchestration mechanism which effectively enforces these decisions by setting up the forwarding rules across the network and actually launching the VMs. And the net effect of doing all of this will be that when suspicious traffic arrives, we can use the power of SDN to flexibly steer traffic to one of these data centers. And inside a data center, we can make sure suspicious traffic goes through the intended sequence of virtual machines, depending on our defense policy. But like I said before, given that SDN and NFV are enablers for what we do, they do not automatically solve the problem. So each of these 3 components are going to be challenging to realize in the presence of an intelligent adversary. So let's just start, for example, with the prediction strategy. So here, remember that we wanted to estimate the attack scenario, the type, the volume, and the ingress point of attack. So if I'm an intelligent attacker and I know how you estimate the attack scenario, I can come up with the complete opposite of what you have decided, so that whatever you've done is going to be ineffective by changing the volume and the ingress point and the type of attack. So how do we deal with them? The second challenge here is going to be about the resource management. Sure enough, there are lots of mathematical and algorithmic platforms to solve a resource management problem optimally. We have tried that, but even for a medium-sized ISP, it's going to take hours to solve. And that is something that we cannot afford in the context of DDoS defense. Because by the time we have the solution, it's going to be too late. The damage is done. So I'm not going to get to the details of our solutions to these 2 challenges. We have designed novel algorithms that can handle intelligent attackers and really, really fast algorithm to solve the problem of resource management. So I invite you to look at the paper for the details. I'm just going to briefly talk about the third challenge, which is about orchestration. But what is the challenge? So let's for a moment imagine we wanted to use SDN just out of the box naively. What is the problem with that? So the way SDN works, if we are not careful about it, is going to be reactive and per flow in terms of forwarding traffic. So here the example is as follows. We have 2 classes of traffic in this case. Maybe one of them is SYN flood, the other is UDP flood. And the policy happens to mandate that green packets need to go through VM1 and VM2, and red packets need to go through VM1 and VM3. That's just a policy, example policy here. So if we use SDN naively, here is what's going to happen. Whenever a packet that belongs to a new flow arrives at the switch needs to talk to the controller to get the forwarding rule, install the forwarding rule, and only then can it send along the packet. And this happens for every packet that belongs to a new flow. Now, if you think about it, there are 2 obvious problems with that in the context of DDoS. By the way, in a benign scenario, that works perfectly fine. But when we're talking about DDoS, if I'm an attacker, I can simply come up with attack traffic that involves a lot of distinct flows. And by doing so, I'm going to impose a significant scalability problem to the system. First of all, I can overwhelm the communication channel between the switch and the control plane because of all these queries to the controller. And the second problem is every switch has a limited space to store forwarding rules. And if there are lots of distinct flows, this limited space is going to be quickly exhausted. So how do we deal with that? So our solution is basically based on tag-based forwarding. So instead of per flow and reactive control, what we do is it's per VM and proactive. So going back to the same example, what we do is as follows. The control plane proactively installs forwarding rules in the data plane. And what I'm showing here is that we have, again, two classes of traffic, but this time VM1 has been instructed to tag traffic in a certain way. So if it is benign, the tag value is 1. If it is suspicious, tag value is 2. And also, if you look at the switch is going to be forwarding traffic just by looking at the tag values. Now, the effect of that is when traffic arrives, first of all, there is no need to have any interaction between the data plane and control plane. And also, if you look at the forwarding table of the switch, now the size of the forwarding table is on the order of number of next hop VMs, which is a function of our policy, as opposed to the number of distinct flows, which is something that attacker could control. So that is how we make the system scalable by using this proactive and per VM tagging scheme. Okay, so we have an open source implementation of the system, and it's available. And the system itself is all based on open source tools like Bro, IP tables, and other custom code. And we've done a lot of evaluation of the system based on the testbed that we have at Carnegie Mellon. And for very large scenarios, we also augmented that with simulations. So here I'm not going to go through the details. Just want to give you 3 high-level takeaways of what we learned from the evaluations. The first lesson was the system actually works, and it works fast. The response time is basically sub-minute up to 1 minute. The second thing we learned is that the system is scalable in that it can handle attacks of up to 500 gigabits per second. And the third lesson was that it can successfully handle dynamic attackers. So remember, these are the attackers that can intelligently change the attack scenario to surprise the system. So we have an algorithm that can provably deal with these kinds of attackers. So the last thing I want to point out here is that we are far from being done. For one thing, what we have is a DDoS mitigation system. So one of the big open challenges is DDoS detection. So I think previous talk was definitely very interesting, and at the same time there are open questions. For example, when it comes to low rate attacks or these stealthy attacks, as far as I know, there are not really very good solutions to sort of detect those attacks. So there are a lot of work to be done here. So with that, I'm open to questions.
Alexander Lemon, Curator Labs. Thank you, very interesting development. Couple of questions. So you said that you're utilizing VMs for mitigation mechanisms, which raises a second question. As far as I know, I'm probably outdated. I'm not a virtual machine guy, but usually VMs used to be not so good processing large volumes of the packets per second because of the costs of virtualization. So how you handle that?
So that's a great question. For the most part, you're right, but at the same time, there is recent research that enables high-rate processing of traffic using virtualized platforms. So, for example, I think if you look at one of the recent papers, it's the best paper in OSDI. They have new development there that enables like 10 Gbps processing. So I think things are getting better on that front.
Awesome. Thank you for update. We'll look it up.
Thank you.
Thank you.
Tim Battles, AT&T. That was actually one of my other questions. But for clarity, you ran 2 different signatures: TCP SYNs and UDP frags.
We have actually 4, just as a as a proof of concept. We have 4 types of attacks.
What were the other two vectors?
So we did elephant flows and we did DNS amplification.
And you did 500 gig and you only had to light up how many VMs?
So in that case, so the 500 was based on, we proportionally increased the number of VMs based on, so we did simulations for that.
Right.
Yes.
Did you have other services running on other VMs, and did you get any collateral damage?
We actually didn't. In our scenario, it was just about DDoS. So we ran our sort of attack scenarios, and we were interested in the response time. So we have an experiment with other applications running at the same time.
All right, thank you.
Yeah.
We're really late, so last question. Go ahead.
Okay, so in the case of 500 gigabits per second attack, and I assume you have this bandwidth, so what's your normal bandwidth utilization? How much underutilized your capacity in the normal life? Because to me, if your normal traffic is around 10 Gs, having extra 100 Gs makes no sense business-wise.
So it was about 50% of the attack. So it was significantly impacted by the attack volume.
Thank you.
Thank you.
Thank you very much. Thank you, Said. Our last talk for this session is going to be given by Luca. Luca is working at IIT CNR, and I believe he's looking for some BGP data and BGP feeds.
Good afternoon, I'm Luca Sani. I am working at the National Research Council of Italy in Pisa, and I'm going to present you Isolario. So our research interest is the analysis and the study of the internet interdomain level ecosystem. This kind of analysis is typically done exploiting BGP data provided by well-known route collector projects. But it is also well known that this data is far from being completely representative of the internet interdomain level ecosystem. The main cause of this incompleteness is that the number of autonomous systems providing a full feed to this project is rather limited. And we believe that one of the causes of this incompleteness may be that not all network administrators are interested enough in sharing their routing information. So for this reason, we tried to propose Isolario, which is a route collector project based on the DODES principle. Indeed, a network administrator that decides to share with us his routing information will receive in change a set of services, ranging from real-time analysis of BGP data to historic analysis. The main aim of Isolario is to contribute to the completeness of the publicly available BGP dataset. So as every other route collector project, we are currently providing collected BGP data in MRT format on our website. In the future, we are also planning to provide some ready-to-use information extracted directly from this data. So the starting point to implement real-time services is a slight modification of the classic concept of route collector. In our system, when BGP data comes into the route collector, it is sent to a dedicated module, a dispatcher, which sends the data on one end to dedicated application modules, which implement the applications, and on the other end, sends the data to a route collecting software, which is responsible for maintaining up the BGP session with the participant, with the feeder, and which also must be able to answer from queries coming from real-time applications. For example, an application may want to retrieve real-time the portion of a given set of routes related to a given prefix. So the route collecting software must be able to answer this query very fast. And this is the big picture of the system. BGP data sent to route collector, it is sent then to the central core of the system, where computationally expensive tasks are executed. For example, a lot of applications require the computation of statistics, and this is where the computation is done. Then the results are provided to users by means of a web server exploiting the WebSocket protocol. So in practice, we provide a real-time stream of BGP data and related statistics that can be accessed through a web browser. The set of services that we make available for participants can be divided into three main categories: real-time services, historic services, and diagnostic services. Now I am going to present to you some of the services available. So real-time services enables a user to monitor in real time BGP data coming into Isolario system. The first service that we developed of this kind is called the routing table viewer, which enables a user to insert a prefix to monitor, and the system will retrieve in real time the portion of the set of routes that his router announced to Isolario in order to reach this prefix. Results are displayed in the form of a table and are correlated with different kind of statistics. For example, there is the AS dependency, which indicates the most important autonomous systems for that user in order to reach the inserted portion of IP space. Another interesting thing that a network administrator may want to be able to analyze is if his router is announcing flapping routes. And this is achieved by the real-time flap detector application, which displays on the web browser the routes that are currently experiencing flap events, where a flap is defined as a sequence of n events in a given amount of time. Again, the results are correlated with the statistics. For example, the type of the flap, if this is a sequence of announcement or an alternation of announcement with drones, etc. And there are also present information about the geolocation of the flapping prefix. Perhaps the most interesting real-time service is the subnet reachability, which is the dual of routing table viewer. With this service, a user is able to monitor in real time the best routes that all the other participants to Isolario are using to reach a given prefix. Even in this case, the results are presented in the form of a table, and whenever there is a new BGP announcement involving one of these routes, the table is updated accordingly. Statistics, in this case, for example, if an user use these services by inserting one of his own prefixes, the ES dependency will take another meaning. It will represent the most important autonomous system for that user to be reached from the outside. So it is like you will be able to monitor your inbound reachability. Since the number of entries in the table may be large, we recently tried to ease the visualization of this information by integrating in this application the real-time version of BGPlay. BGPlay is an open source tool for the visualization of BGP routing events, and thanks to the collaboration with its author, Massimo Candela, we managed to integrate it in this application. So this is the main view of BGPlay. Red nodes are the nodes originating the monitored prefix. Blue nodes are the nodes connected to the collector, in this case to the route collectors of Isolario. And black nodes are all the other autonomous systems. The basic graph is built on the basis of the information retrieved from the route collecting software, which contains the most updated routes to reach the monitored prefix. And then whenever a BGP announcement occurs, an animation is triggered resembling the transition to the new status. For example, an autonomous system path may be constructed and another may be destroyed. So autonomous system paths involved in some network change, are represented by straight lines, while autonomous system paths not involved in any change are represented by dashed lines. And this approach enables an user to see at a glance if which are the autonomous system paths stable and which are the autonomous system path not stable. Whenever a BGP announcement occurs, the graph is updated accordingly in real time. So basically, this version of BGPlay is connected to our WebSocket streaming. Another class of services is the class of diagnostic services. These services have the purpose to enable a user to be informed about network anomalies without the need to being directly connected to the Isolario website. So the first of these services is the alerting system. With this service, a user is able to set up a different kind of alarms and be advertised when a network anomaly happen. For example, a user may want to be advertised when one of his router is announcing to Isolario a route toward a particular destination containing a particular subsequence of autonomous system into the autonomous system path. As another example, he may want to be advertised when a destination of interest is no more reachable by his router, or when one of his own networks is being announced by an illegitimate origin. And notification will be sent to the user through mail or through post, for example, to dedicated web servers. Then there is the daily report, which is a document which is computed once per day, exploiting all the BGP data available. So the BGP data collected by Isolario, but also by all the other route collector projects, route views, RIPERIs, and PCH. The main aim of this application, this report, is to provide the user information for network anomalies that may go unnoticed. So, for example, you can see into the document information about the reachability of the whole IP space from the perspective of your routers. You can see information about the stability of routes, which are the most stable and stable routes, and also information about the routes containing anomalous BGP attributes, for example, routes containing loops into the autonomous system path or private autonomous systems. Finally, you can also have information about your inbound reachability as it is perceived by all the feeders participating to all the route collector projects. And finally, there will be available historic services, which will be the historic counterpart of real-time services. And they will exploit, in this case, again, like the daily report, all the BGP data available. So for example, there will be available an historic routing table viewer as well as an historic subnet reachability. So the idea is to help the network administrator to troubleshoot interdomain level ecosystem issues. So in summary, this is how you can use Isolario. You can be advertised if something is happening thanks to the alerting system. You can notice some anomaly by reading the daily report. You can troubleshoot. You will be able to troubleshoot that anomaly exploiting the historic services, and maybe you can check in real time if the anomaly is gone, exploiting the real-time services. So that's all. If you want, you can try Isolario by accessing with the guest credentials through our website. And that's all. If you have questions, they are welcome.
So does the system rely just on live information, or can it use all of the information from route views and other sources as well?
Real-time services rely only on live information coming from feeders connected to Isolario. Historic services and the daily report rely on all the data available to the public. So.
Any other questions? Thank you, Luca. That was the last presentation of the session. Thanks to everyone for coming to the Research and Education track. Next up will be the peering personals, and also a reminder about the social tonight, which is going to be offsite. Thanks, everyone.